Welcome back to another dazzling pre-class video. This time we'll be talking about nonlinear systems of equations. As you might expect, a nonlinear equation is one that is not linear. That means any equation that cannot be written as some number times x plus another number times y equals a third number. Anything else is considered nonlinear. That means anything that includes other powers, like a quadratic equation, or this is the equation for a circle, definitely not a straight line, not a linear equation. Things that have square roots or logarithms. A square root is the same thing as an x to the 1/2, so that's definitely not linear either. All of these are nonlinear equations, but that doesn't mean we can't solve them still. A system of equations is called a nonlinear system if at least one of the equations in there is itself a nonlinear equation. And so the strategies for solving these will end up being very similar to our linear systems, with the exception that the order we do these steps might matter. Specifically, we learned two techniques in class last time, substitution and addition, and those are still going to be our friends. Let's take a look. Say we want to solve this system of equations, x minus y equals -1, and y equals x squared plus 1. Although we could graph these if we want, we could see that one of them is a straight line, the other one is a parabola. Instead, we can use the technique of substitution, where we know that y is equal to x squared plus 1, and so we could plug that into the y of our other equation. That gives us a slightly messier equation, x minus the whole thing, x squared plus 1, equals -1. If we go ahead and rewrite this, we could get negative x squared plus x minus 1 equals -1, or therefore, if we factor out an x, we could get x times negative x plus 1 equals 0. Notably, these minus 1s ended up canceling. Since we have a already factored quadratic equation, we can now solve this, giving us two solutions, x equals 0, or negative x plus 1 equals 0. That is, x equals +1. Now that we have two solutions, we have two choices. Technically, we can plug these into either of these equations, and they will both give us the correct answer. However, in some cases, plugging equations into the nonlinear equation can result in what's called an extraneous solution, or a solution that doesn't actually show up. And so I'm going to plug them into the linear equation and suggest that you do the same if you have one. Plugging in x equals 0 into this first equation, we have 0 minus y equals -1. That is, y equals 1. And plugging the x equals 1 in, 1 minus y equals -1. Therefore, y equals 2. This gives us two solutions, 0, 1, and 1, 2. Notably, we do actually get the same thing in this case if we plugged it into this equation. So to be safe, we should always check by verifying that these solutions in fact satisfy both equations. But often the linear one is enough. Let's try one more example. This time we're looking at the equation of a circle, x squared plus y squared equals 26, and an ellipse, 3x squared plus 25y squared equals 100. Well, we could solve one of these equations for x or y and plug it into the other one using substitution. In this case, I think addition or subtraction is going to serve us a little better. Let's say we take this entire equation and multiply it by 3. That will give us 3x squared plus 3y squared equals 78. At this point, we could subtract these two equations. Notably, 3x squared minus 3x squared ends up canceling, and what we're left with is a much nicer 22y squared equals 22. At this point, we can solve for y, divide both sides by 22, we get y squared equals 1, and we have to be very careful here. This is where extraneous roots can pop up. This gives us not just y equals 1, but plus or minus 1. There are actually two solutions here that we have to consider. So we'll write them both, y equals 1 and y equals negative 1. At this point, it doesn't matter which equation we plug it into, they're both nonlinear, so I'm going to choose the simpler one. If we plug in y equals 1 into this first one, x squared plus 1 squared equals 26. That means x squared equals 25, or therefore x equals plus or minus 5. It turns out, because of the properties of negative numbers, when we plug in y equals negative 1, x squared plus negative 1 squared equals 26. That's the same thing as x squared equals 25. Y squared was still equal to 1 in both of these cases, and so therefore we get the same roots, x equals plus or minus 5. This actually has 4 unique solutions: 5, 1, 5, negative 1, negative 5, 1, and negative 5, negative 1, which you can verify graphically if you like, but it's always worth it to check that all of these solutions satisfy all the equations that you're given for it to be considered a valid solution. In class, we will practice solving these nonlinear systems. We'll write and solve some word problems involving nonlinear systems. We'll also talk about solving a system of inequalities, and finally talk about mid-course evaluations. See you there.